talk of the day. It's about asymptotically good Lex locally correctable codes with slope squared queries. Almost 2 orders of magnitude improvement of the exponent, very impressive. And work it by Yankovitz and Cohen and Talon Gilbert.
Hi. As Yuval said, this a joint work with Gil Cohen. Luckily, the previous talk already defined and motivated. Even so, I wrote down. So this is the definition for a locally correctable code, a Q delta locally correctable code. So if there should exist some randomized procedure that if the given string is a distance at most delta from some code word, then the requirement is that for every index j, the procedure is able to correct C at location j with a good enough probability. In the case of locally decodable codes, we require the same, but this time we are looking to decode a bit of the message rather than the code word. And in what way do we relax here? Following the definition by Ben Sasson, Harsha, Sudan, and Vadan in 2006. Well, we just say that if essentially if the decoder or the corrector found out that there is some error in the word, then they may output a special symbol that means abort. So the requirement is that for every noisy string at proximity at most delta from some code word, we either output a bit of the code word, the right bit, or abort it probability 2/3 with this further requirement that says that if we get a true code word without any errors, then the procedure must not abort. Okay, so and the relaxation of RLCC, I didn't write it, but it's clear. Okay, so the same history as in the previous talk. So first of all, what is the lower bound for high rate? When I say high, I mean at least a constant. So at least omega tilde of a square root log n by the beautiful lower bound that of the work of Gur and Lachish. They are able to show it even though things are quite different from locally decodable codes. They are still able to show this lower bound. It's nice. So Gur and Marayan and Rotlum, with the tensor construction, they achieve this square complexity, the same as the previous up until the recent breakthrough, the best high rate locally testable codes, so with the same query complexity. And we, in a past work, were able to remove one log factor from the exponent, the talk we heard now, Kumar and Mon. So this 69 that we all remember. So I wrote O tilde of log n squared because non-explicitly this is what we get. The plus little of 1 is if you insist that the code is explicit. So in this talk, I will disregard explicitness. Okay. So for LDC, just to remind that the lower bound by Katz and Travis for LDC and also for LCC. So this is both for relaxed locally decodable codes and relaxed locally correctable codes, because all these results, so this holds for relaxed locally decodable code, and all of these are true for relaxed locally correctable codes, and essentially local correction is harder. Okay, so it's good, the lower bound is for the object that is weaker, and the upper bounds are for the stronger object, so this is good. So for the case for LDC is that Q must be at least log n, and it is possible to have 2 with this square root log n by the work of Koparty, Meir, Rontzvi, and The lower bound? Logn? Oh, the Katz and Trevisan. Yeah, and I think maybe by Rudolph also from 07. Okay. And this is, by the way, quite significantly, should be, there is a log-logn factor. So this is quite below a polynomial. It's smaller than a polynomial, and this came after, and together, so this is multiplicity codes, which are Reed-Muller codes with derivatives, and with the idea to perform a distance amplification. So this is nice, and also with this and multiplicity codes, and later also other work, they sort of broke down this long years in which there were not known even any non-trivial locally decodable codes with a rate that is above 1/2, and of course nothing with subpolynomial query complexity. So important, but since then we don't know of a progress for LDC or LCC with high rate. Maybe some. Okay. So I want to say, okay, so we in this talk I'm going to show this. So let me just say that these are binary codes. So if you care about it, and also the rate that we get has because the query complexity is so small, then you can also start to care about other parameters. So what is the rate versus distance trade-off? It gets close to the Gilbert-Verschamow bound. Okay, there is some multiplicative factor of a constant, but it gets close to the okay, non-explicitly, and also explicitly it is similar. Okay, so yeah, you get a similar behavior, right? Gilbert-Verschamow you get if when delta goes to 0 is delta log 1 over delta. So instead of log 1 over delta, you get quasi-poly log over 1 over delta. Okay. So I just want to make a remark about this square here and the fact that for locally decodable codes, the lower bound is log n. So there is like a question. Can we show a bound of that Q must be omega of log n to the 1 plus epsilon for a good RLCC. So maybe for any constant. So it's an open problem to strengthen this bound for locally decodable or locally correctable code. So is it possible that we can improve this bound only by using the fact that the code is a relaxed locally correctable code? So there is still some tension because the current state of affairs is that the lower bound for the strong object doesn't even reach the upper bound for the weaker object. And the exact power of the exponent, it does matter sometimes a bit. For example, there is a work by Dvir from 2010, which says that if you can show that for a good LCC, it must be that Q is at least omega of log n to the 2 plus epsilon for any epsilon, then you get some implications for matrix rigidity that are unknown.
It's still unknown because the work was some progress. So
well, according to a paper from 20, I think still unknown. Yeah, that as far as I know. So at least our work disqualifies the hope to get only from relaxed locally decodable codes this implications. But it is still possible, like if you are sometimes in an exam and you get a question, and in the question you find out that there is an extra assumption, like that you are given. Sometimes it becomes easier if you don't need to use it. So maybe the extra assumption for it could be. So I urge you, please try, because it is interesting. So between square root and 2, still open. Okay, so let's give a square root logn sounds weird. I guess it should be logn, but I don't know. Okay, so in order to say how we get the query complexity, I want to start with recalling the beautiful reduction that we just saw. But I'm probably going to say it in a way that is a bit different from what Jeffrey said. So the Kumar and Mon reduction. So I will need to, I should have written it down, but again, delete here. I will need to write again the definition of locally testable code, which we know, but still. Okay, so we say that C is a Q tau LTC if there is some procedure A that satisfies the two requirements. One is that A of C, for C in C, always accepts. And for a string Z, A rejects with a probability that it is tau proportional to the distance of Z from the code. So Dinur, Evra, Lubotsky, Moses, and also Pantlir and Parashev show that C to the 3 good codes, good LTC exist. And also, as an implication from the work of by Dinur et al., they are not only, they can also be used in order to get codes with high rate with poly-logarithmic query complexity. So these are LTCs. And the Kumar-Mon reduction, which is from LTC, means that essentially LTC give RLCC. It says, okay, take a sequence of partitions. Okay, so there are logn partitions. P1, P2, P logn. So probably I'm going to say it in a way that is a bit different than what we saw. So we have some, we think of, so there are partitions of the set of coordinates n. Okay, so we have a world n. And also, every partition is going to be a subpartition of the next partition. Okay, so the biggest partition, I guess P logn, is just one part, the entire world. And there is also a smaller partition which has 2 parts, and there is another partition which has 4 parts. And by subpartition, we mean that, so always, that's a refinement of the, okay, so we take such logn partitions, and we also take logn LTCs. C1, C2, C logn. So in what do they differ? They differ in the block size. Okay, so the block size of C1 is going to be the same as the part size of P1, and C logn is going to have a small block size like the part size of P logn. Okay, so what is the code? So the final code, it's really very simple. Is all the strings, let's say, binary alphabet such that for every partition, for every part within the partition, we have that the string projected to the part is a valid code word of the ice code. Okay, so these are just all the strings such that here, this is the code word of the locally testable codes, here too, and so on. So why does this give an RLCC? We can just describe the correction procedure, right? So RLCC. So we are given some j, and we need to correct. So what do? Well, we just we verify, we check. I didn't say if there are any questions, please feel free to. Okay, we check that. So let b1 to b logn be the parts of the index. Okay, so j is in all of them. So we just check that all of them are close. That okay, we are also given some string. Okay, some string in which we want to correct the index j, and we check that z reduced to b1. That for every I, z reduced to bi is close to ci by applying the testing of the LTCs. So that's the idea. So now, if somebody, okay, so that's the correction process. And so since they are logn codes, essentially the query complexity of we up to a factor of logn, the query complexity is inherited from the LTCs. Okay, so why is this correct? What's the correctness? So we see that if, so I didn't say eventually, if one of the checks, if a check failed, let's say if all checks passed, we make an extra query, and we output C at location J, and otherwise, we output abort. Oh, yeah. Thank you. Okay, so why is it correct? So we see that we only need to handle the case that Z at location J is different from C at location J. Otherwise, we are always successful. Right, so assume that Zj is not equal to Cj. So we argue that there must exist some partition, some index of a partition such that the following holds. The distance of Z reduced to the Bi part and Ci is between delta and delta over 2. Why is this true? Well, because we are only assuming that we are within the correction radius, right? So if we consider the largest code, then we do have the right-hand side satisfied. But since we assume that here Zj is different from Cj, then there is a change in this part, and this is very small, right? So as long as the smallest code is at size at most 1 over delta, then maybe a factor of 2, then this holds for the smallest, right? So there must be some index where this step occurs, right? So, and this is important because in relaxed, locally correctable or decodable codes, sometimes you want there to be many errors. If there are very few errors, sometimes it's not a good position to be at, because many errors mean that you have a good chance of catching them, right? So on the one hand, we are in a good promise, not too many errors. On the other hand, there are enough errors so we can catch them. Okay, so as long as we make enough queries, we will see a mismatch. Okay, so that's the idea behind the correctness. So now let's ask. Because if we allow for a very large number of errors, for example, somebody can always just move us to another valid code word, and then we will fail. So let's ask if is LTC really needed? The same sort of like this progress came after the breakthrough in the world of LTC, even though this object existed before. So it's a good question to ask. So what is the thing about LTCs? Well, they are maybe hard because they are required to work, even if, so this is the word and these are code words. So even if we get some string that is very far from every word, from every code word. And this is sort of part of what makes it hard, right? But what if we only consider the cases that we are not given something that is too far, only something that is quite close to the code? And we see it is written here, that there is some bound on how far we are. Okay, so let me just define. So I'll just add to definition of an LTC what we define. So we say that a code is a Q tau delta. We call it vicinity LTC. It's essentially, it's very similar. We only add here that we reject with a probability that is proportional to the distance if the distance of z from the code is at most delta. That's it. So is it easy to construct this object, easier than LTCs? Well, yeah. So what are expander codes? I guess we know. But first, let me say what are unique neighbor expanders. So G, which is a bipartite graph, is a gamma alpha unique neighbor expander. If for every set on the left side that is not too large, the number of unique neighbors of the set, so n unique, is at least alpha times the size of the set. We have some set. So a unique neighbor of the set is just a vertex on the right side that is only adjacent to one vertex in the set. So these are unique neighbor expanders. And what are expander codes? So the expander code associated with the graph G is just, so it lives in 0, 1, to the L. So we write bits on the vertices of the left side. And we take C to be all the strings such that if we take every vertex on the right side and sum it up, we get 0. Okay, so on the right side, the sum over U of V. So these codes were defined by Sipsper and Spielmann in '96. So, I guess we also saw other expander codes today, the ones that are, we have bits on the edges, but here we have bits on the vertices. Okay, okay, so let's, so these are very, very simple codes, and as was shown by Sipsper and Spielmann, they have the great advantage of having a linear time decoding. So let's argue. We defined VLTC somewhere here. Let's argue that these expander codes are VLTC. So if G is a gamma alpha unique neighbor expander, so let's also say that G is a DQ. Let's assume that the left side is of size n. Then the code C is a Q alpha Q over D gamma VLTC. So this is the query complexity. This is our tau, how much, what is the proportion to reject. And this is the delta of the VLTC when we are good. Okay. So this is a very simple claim. It can also be seen as an implication of the decoding algorithm by Sipsper and Spielmann, but this is, we can prove it very simply. Okay, so let's prove it. So in order to show that the code is vicinity locally testable, we need to show that we indeed reject with a probability that's proportional to the distance as long as the distance is not too far. So let's take some word Z. So, and let's assume that the distance of Z from the code is smaller than gamma, because this is the promise that we are arguing for. Let's draw the graph. Okay, so we. Oh. It's like a riddle. Oh, it doesn't go. Okay, okay, good. I will swap if we need something. Okay, so we can also take some word C that is of minimal, that is closest to Z. And we also have that the distance of Z from C is at most gamma, right? So how can we show that it is indeed a VLTC? Well, we need to describe a check. So what is the check? Any guesses? Well, what can we do? We are going to sample a random vertex on the right side, and we are going to check that the sum is 0. Right. So what is the probability that we reject? We want it to be high. So we need to somewhere use the assumption that G is a unique neighbor expander. So we need to take some set on the left side. So what set are we going to take? We are just going to take the set of all indexes such that Z differs from C. And we see that any unique neighbor expander, so any unique neighbor of the set that we chose is going to cause us to successfully reject, right? Because if it sounds interesting. So, right, so if we have some vertex on the right side, and it only has one neighbor inside our set, then we see that the XOR is going to be 1 and not 0, right? So the probability that we reject, so rejection probability is at least the number of unique neighbors divided by R. So they are at least alpha times the size of the set. So I also, because this is a relative distance, so this is the size. So if we just replace this, so what we get, to get exactly what I wrote, we just need to replace L over R by, so this is the distance. We need to replace it by, this is the same, right? The relation between the size of the two sides is opposite to the relation between the degrees. So that's it. So what is the rate of these codes? Well, the number of constraints is R, the size of the left side. So the rate is 1 minus D over Q, right? Because it is R over L. So what are, I think I said what I want to say. So let's conclude to see what is the query complexity that we get. Oh, so I need to say that unique neighbor expander exists. So this will show that VLTC exists. But actually, so there are explicit constructions that are quite good. The CRVW construction, for example. But non-explicitly, so let's say fact. So for every n is the length of the left side. There are QD regular. Neighbor expanders. So what are the parameters? So we want D to be as small as possible. So let's say that we Q is to our choosing. So also for every Q. So what we have non-explicitly is that D is order of log Q. And gamma is omega of 1 over Q. So this is non-explicitly. So we can use this to get the unique neighbor expanders that we want. Okay. So So because yeah.
What's the imbalances that you need? So what's L over R or here?
So L over R. So that's a good question. So this is the imbalance. So the rate that we get is for each one of the VLTCs is because this D is roughly log Q. So we are shooting for poly-logarithmic correct complexity. So log Q is going to be log n, right? So we are going to get 1 minus log Q over Q. So if we take Q to be log n, we get 1 minus log n over log n. So we need to take Q to be slightly higher. We'll take it to be log n times log n. Right. So, okay, so let's conclude. So we choose. So this was a sort of a repeating theme in the previous talks. We just the rate that we get is we calculate it by counting constraints. So we have log n codes, and we want the final code to be subjected to the constraints by all of them. So eventually, the correct complexity that the rate that we're going to get is going to be 1 minus log n times d over q. And d is, as we said, is log q. So we are going to choose q, which is roughly log n times log. Okay, so we get a rate omega of 1. And the query complexity is, as before, there are now log n phases. The check is just the same as before. And each one, the query complexity is inherited by the right degree. So it is just q. So q is log n times log n. So the query complexity is log n squared times log n. So one thing to note that is that we shoot for a code with a constant distance, and these codes have a distance of 1 over log n. So the final step is to take. We just need to. The only change we need to make in order to end up with a code with a constant distance is to take the last code to be to use unique neighbor expanders with parameters that are that give us a constant distance code. So and why does this work? Just you can think that maybe you needed to do distance amplification or something like this in order to amplify your distance, because there are two options, right? Either the number of errors is smaller than 1 over log n, or it's more. If it is smaller than 1 over log n, great. The smaller codes are going to handle it because you are within their promise, right? But if there are more than 1 over log n errors, then the last code can catch the errors, right? Because you only need to make log n repetitions, and then you have a good probability of catching the errors. So no distance amplification is needed here. Just take the last code to be a code with a good distance. And maybe sometimes I say distance, I mean like it also affects the distance of the code, but what I mean is the promise of the VLTC. Okay, there is also some relation to the distance of the code, of course. So what I want to, so the conclusion eventually is that we can construct very good relaxed locally correctable codes, and therefore also relaxed locally decodable codes, only by using these very simple codes defined by Sipser and Spinman in '96. Okay, so you may say, but in order to have an explicit construction, then you need good unique neighbor expanders, and you are right. So good enough such expanders were constructed by CRVW in '06. But let me just say that you can also, if so the code here is very simple, and I guess it can be useful for some applications. Really very simple. So if we want to optimize simplicity, we can also, for example, take some other expander, for example, a Cayley graph, when used with some epsilon bias set, which we can take, for example, as the one from the code of that is Reed-Solomon concatenated with Hadamard, and then we get a higher query complexity. Instead of log n squared, we get log n to the fifth. So still quite low, and yet very, very simple. Like all these codes from the 70s, they still give. So this is the, I guess. Okay, so actually my so I'll be happy to hear if there are questions, but my two open questions for everybody to solve are exactly the same as the one that Jeffrey said in the previous talk. So two open questions. One is either improve the lower bound or construct better codes. And the second one is try to have a code with a query complexity that is lower than log n to the log n, while being both relaxed, locally decodable or correctable, and locally testable. We don't know how to do it, and it's interesting and important. Okay.
Okay, there's time for quick questions.
Can some improved VLTC help you improve the query complexity?
Oh, I think the VLTC that we got here are essentially optimal, because it's probably the number of queries that you need to make should be at least 1 over the distance, 1 over delta. And so here the trade-off that they get is, so essentially by the Gilbert version of bound or something like this, you cannot make, so this is an optimal trade-off.
Any other questions? Okay, so same time again.